Preparing to live stream the meeting. Just give it 1 second. Seems it's just YouTube side now. Okay, I believe that we are on.
Welcome everyone to the 2021-22 Keyfitz lecture. My name is Kumar Murthy. I'm the director of the Fields Institute. Let me begin by acknowledging the land on which the Fields Institute operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. As some of you may be participating from elsewhere, may we suggest that you research the history of your land using the website nativeland.ca or an equivalent site in your region. Once again, my name is Kumar Murthy. I'm the director of the Fields Institute. Many of you, I think, are familiar with the Fields Institute. But for those who are new, we are a network of about 20 universities, principal sponsoring and affiliated universities. We do research in the mathematical sciences in the broadest possible sense, spanning from basic fundamental research to applied and even industrial research. We're funded by the federal government of Canada through the Natural Sciences and Engineering Research Council, through the Canadian Institute for Health Research, by the province of Ontario through the Ministry of Colleges and Universities, and through the foundations in America, the National Science Foundation and the Simons Foundation, and also by individual generous donors such as yourselves. The Fields Institute hosts many programs, thematic, long-term and short-term programs, and it is our pleasure to host the annual Keyfitz lecture. Now, Keyfitz is a name that people who are familiar with the Fields Institute will know very well. Barbara Keyfitz was director of the Fields Institute from 2004 to 2008. She's currently professor of mathematics at the Ohio State University. Her father, Nathan Keyfitz, was also a well-known mathematician. Mathematics runs in her family. Nathan Keyfitz was a mathematical demographer, a pioneer of this area in Canada. He graduated from McGill University, and over the course of his career, he held positions at the University of Toronto, the University of Chicago, Berkeley, Harvard, and also at the Ohio State University. He was a fellow of the Royal Society of Canada and of the National Academy of Sciences in the United States, a very distinguished scholar. It's his generosity and also the generosity of Barbara that has led to an endowment of the Keyfitz lectureship, in which the idea is to discuss mathematics in the context of its application to social sciences. The first lecture was given in 2007, so that would make this the 14th lecture. I say 14th and not the 15th because this is really the 2021 Keyfitz lecture. You see, normally the lecture is held in May of the year, but both the pandemic and schedules of our speaker have caused it to be delayed to now, but anyway, we're happy that we have actually now been able to hold it. Our very distinguished speaker today is Professor Adrian Raftery. He's the Boeing International Professor of Statistics and Sociology at the University of Washington, a highly cited researcher, also a fellow of the National Academy of Sciences in the United States. And he is a pioneer in new statistical methods for social, environmental, and health sciences. I just know we're going to really be thrilled and delighted to listen to his thoughts today. He's going to speak to us on very long-term probabilistic population projections. Those of you who are joining us on YouTube, there will be an opportunity for a brief question and answer. If you do have questions you'd like to direct to the speaker, please put them in the YouTube chat. We don't guarantee that we'll be able to get to all of the questions, but I know Adrian is eager to engage, and so we will try to get to as many as we can within the time constraint. So without further ado, please, Adrian, would you we're eager to hear your thoughts on the subject.
Well, thanks very much indeed, Kumar. It's a great honor and pleasure to be here. Of course, the Fields Institute is a major institution, so this is a very prestigious invitation. But beyond that, I like to think that maybe this is particularly appropriate because Nathan Keyfitz was possibly the leading demographer of the 20th century, certainly the leading mathematical demographer of the 20th century, and among many other contributions, he was actually the first demographer to call for the development of probabilistic population projections, and the first person to actually produce probabilistic population projections. And so this was really gave a kickstart to the area that I'm going to be talking about today. So my topic is very long-term probabilistic population projections, and the motivation which I'll talk about for this is as part of the assessment of the social cost of carbon in the United States. This is joint work with Hanna Shevchikova of the University of Washington, and it's in cooperation, long-term cooperation with the United Nations Population Division, with whom we've develop some of these methods, and also more recently the Resources for the Future, which is a think tank in Washington DC that has been working on assessing the social cost of carbon.
I think you started the thing on a different link.
Oh no.
So start.
So I'm hearing some. I'm hearing some discussion in the background, but anyway, I will proceed unless I'm told otherwise. So this work, I want to acknowledge the very long-term research support and substantial research support of the Eunice Kennedy Shriver National Institute for Child Health and Human Development, or NICHD, which is one of the institutes of the United States, NIH, National Institutes for Health. So the background here, why are we interested in very long-term probabilistic population projections? The population projections is the main reason. The number one use of population projections is for planning, particularly government planning, but also private sector, and that really goes maybe to the end of the century. But here we're looking at even longer population projections, which are important as part of the assessment of the social cost of carbon. So this is an estimate of the economic costs of an incremental ton of CO2 emissions, and it's a fundamental number. It's used in policy analysis across the US federal government, and beyond that, every project that's carried out by the US federal government by law must have an assessment that incorporates the cost of the carbon that will be emitted. And that means that it has a huge impact. The US federal government is a huge organization. It probably accounts for about something like 10% of world GDP in total. So just in what it does, it's a huge contributor to carbon emissions, and what it does to limit them has a huge direct effect on world carbon emissions, but also by example, by regulation and so on. What it decides is extremely important. And probably some of you may have been following political events in the United States where the Biden administration proposed the so-called Build Back Better bill, which had a huge component for addressing the climate change issues, and that did not succeed in the US Senate. But actually the social cost of carbon, which is a far less visible quantity, probably has an impact that may be comparable in some ways to that of the the measures proposed in the Build Back Better bill. So it's a kind of below the radar kind of number, but something that probably has a gigantic worldwide impact on the future course of efforts to address climate change. The history of that is it became law, I think, in the Obama administration, or maybe even before. Under the Obama administration, the social cost of carbon was estimated as about $41, I think, per ton of CO2. One component of that is the discounting rate that's used. The Trump administration was not very favorable to taking account of the social cost of carbon in decision making, but by law they had to. So what they did was they increased the discount rate to the maximum allowed, which was 7%, and that reduced the social cost of carbon hugely, I think maybe to $2 or $3 per ton. So temporarily the Biden administration has reinstated the previous Obama era number, and is currently engaged in an evaluation project to update that, and the number that is decided on will have huge, certainly American and probably global impact on the course of climate change mitigation efforts. The National Academies in the United States, the National Academies of Science, Engineering and Medicine, issued a 2017 report on the methodology for this, and they recommended improving the representation of key input variables, and particularly characterizing uncertainty probabilistically. And previously in this era, in this area, uncertainty, if it was characterized at all, it was using scenarios. And I will have something to say about scenarios, which I think are quite widely felt not to be the best way to proceed about assessing or incorporating uncertainty. So they recommended an integrated modular framework, the use of probabilistic population and GDP projections, which is the topic of my talk today, the use of a physical climate system, the updated state-of-the-art damage functions, and of course a discounting approach. So the US administration has accepted this broad approach, and the work that I'm talking about is within this framework. So the Biden administration is updating its social cost of carbon estimation methodology to include the best science in line with the recommendations of the National Academies, and it's aiming for updated estimates soon, and certainly probably within the first half of 2022. So we're talking about work here that is on the cusp of being brought into practice. So the modular framework here is basically, there's a socioeconomic module which feeds into a climate module, which feeds into a damages module, which feeds into a discounting module. And basically the idea is that population, GDP, and carbon emissions basically, well, they feed into carbon emissions, which in turn has an impact on the climate, and that in turn causes damages, which get discounted depending on when they happen. And so this is looking at what's the impact of a single CO2 pulse, a single ton of CO2 emitted into the atmosphere. Population is very important here, both for projecting forward what will happen in terms of emissions, but also in the future for looking at what the damages are, because damages are incurred, at least in large part, by people, and so it depends on the number of people in the future. These calculations are challenging, particularly because we're looking at a very long time horizon. CO2 is one of the kind of tragedies that, what we've done, and CO2, once it gets emitted into the atmosphere, it stays there for a very, very long time, for centuries, possibly even millennia. So once you emit carbon, and to a lesser extent other methane, other greenhouse gases, you basically can't undo it. It's there. And so you have to look, the damages are over a very long term, so you have to look over a very long term. And somewhat arbitrarily, well, both the National Academy of Sciences recommended and the US administration has accepted 2300 as a kind of a stopping date. The idea being that with discounting, the damages will continue past 2300, but they will be, discounted enough that they can be ignored. And there's some things here which I'm not going to be addressing, but basically my talk is about this part here of the whole process, which to some extent is driving the whole thing, because the damages are proportional to population and how population evolves over the long run. So I want to talk about population projections in practice. Talk about how they're done, the recent developments and movement towards probabilistic population projections worldwide. And then in the last part of the talk, I will talk specifically about the going to 2300 rather than 2100. So population projections, of course, are used by governments at all levels for planning, also by the private sector and by researchers, particularly in the health and social sciences. And one can think they're very, very widely used. It's quite possible that, population projections are the single most impactful contribution of the social sciences as a whole to society. Certainly, they're up there as one of the top ones. The organization that the main organization that publishes population projections for all countries that have official status and are updated on a regular basis is the United Nations, specifically the United Nations Population Division, which publishes projections of age and sex-specific population counts and vital rates, by which I mean fertility rates, mortality rates, and international migration rates for all countries by 5-year age groups in 5-year periods. They estimate them back to 1950, and they project them forward from the present to 2100. And these projections are updated every 2 years in a publication called the World Population Prospects. And the reason that the official reason why this effort is funded and done on such a regular basis is produced by the UN for the UN. So they're used throughout the UN system, but they're used, for example, as inputs for development planning, for monitoring, like monitoring the Sustainable Development Goals, which are 2030, and also for global modeling, for example, climate modeling, food security, and so on. And they're often used, countries that have their own well-developed statistical systems, like Canada, for example, they do their own population projections. But there are many countries that don't have this level of resource for, don't have such well-resourced statistical systems, and they often use the UN projections for their own planning. And the last revision was in 2019, which was published in mid-2019. Actually, we're now in 2022. The reason for that lag, which would be a 3-year lag, there'll be a version published this year, is because of the pandemic. The UN wants to be able to take account of the latest information about COVID in its population estimates and projections. And the traditionally, as I'll be talking about for many decades, population projections have been done deterministically. And starting in 2005, we started this research project, which was in collaboration with the United Nations and in cooperation with the UN, I should say, to develop probabilistic methods for population projections. And in 2015, for the first time, these were adopted as the basis for the UN's official population projections for all countries. And since then, of course, the methods have been being developed and improved. Now, one thing is, you might say, is this crazy? Does it make it's? If you think of many things, for example, forecasting the unemployment rate or inflation, the stock market, it wouldn't be feasible to project that 2100, there'd be no hope of forecasting that anyway reliably into 2100. So why do we imagine that we can do that with population? Well, actually, if you think of 2100, there's a lot of inertia in population as a system. The real unit of time is the generation, which is about 27 years. So the year 2100 is actually about 3 generations into the future. So in terms of how far that is into the future, it's about 3 time points into the future, which no longer seems quite so implausible. And one can do good population forecasts well into the future using current and recent population numbers and vital rates. So governments do this depending on the country. Ireland, a small country, for example, where I happen to come from myself, the Irish government projects population about 1 generation into the future, which is more or less just about enough for government planning purposes. The US Census Bureau goes to 2060, the European Union to 2070. The US Social Security Administration, which looks at old age provision, pensions and so on, public pensions in the United States, goes 75 years into the future, so to 2095, which is necessary for calculations of solvency and premiums and so on. And the Japan does go to 2100. The UN projects to 2100 because it has responsibilities beyond government planning, and this is for looking and informing the global conversation about various global trends, climate modeling, food security, and other questions. And the UN's record of population forecasting is actually quite enviable. For example, from the first time, the UN basically from 1950 onwards, it's been doing population forecasts. And in 1958, for the first time, they did a population forecast that went into the 21st century. So they forecasted a population in the year 2000. And it turned out that period of 42 years was a very difficult period to forecast because world population was actually increasing faster than it ever had before. It was a very turbulent time, if you like, demographically. So forecasting extremely difficult if you look at the 1958 perspective. World population more than doubled in that period. So one would think that any forecast could be way off, but the UN's 1958 projection of the world population in 2000 was actually accurate to within 4%, which is extremely impressive. The members of the UN Population Division, they're very good scientists and they're very modest about their achievements. So whenever this is pointed out, they immediately say, oh yes, but if you look at individual countries, the errors were a lot bigger. So, when one looks at individual countries, there's quite a lot more uncertainty than this. Okay, so what are the traditional methods for doing this? So starting more or less in the 1940s, the traditional method was introduced by a United States demographer called Pascal Whelpton, and who in the 1930s and was adopted by the US Census Bureau in the 1940s, and became, after World War II, became a kind of global standard. And it starts from current population estimates and projects population forwards deterministically using the cohort component method. And this is a very simple method. It takes future fertility, mortality, and migration rates, and basically you calculate births and deaths and migrations and add or subtract them from the population in each age appropriately. And there's some very nice mathematics about that, of which Nathan Keyfitz was actually one of the leading exponents. So this is a method that is easy to interpret, easy to implement. So what's the catch? And one of the Achilles heel of this method is that it requires assumptions. It's a perfect method if you know future fertility, mortality, and migration rates. In practice, of course, we don't, so it requires assumptions about them. And where do these assumptions come from? Well, in practice, in this method, they're produced by experts. in many cases by in-house experts. The UN and the US Census Bureau basically use their own people to produce these assumptions. And some countries like Germany, for example, use expert panels where they mobilize, in the case of Germany, leading German demographers, economists, mathematicians, statisticians, and so on, to say, we think the fertility rate in 2070 will be, 1.7. And then uncertainty is communicated. We're used in the modern era to communicating uncertainty in statistical ways by things like confidence intervals, standard errors, and so on. However, traditionally, population projections, they go back before that era of where statistical uncertainty was pervasive and standard, and uncertainty was communicated instead by scenarios. And I'll be criticizing that approach, which is, I think, and also kind of channeling a consensus in the certainly academic community, but I'll describe it. And the UN traditionally, before going probabilistic, published high, medium, and low variance. So the medium variant was what came from experts. The high variant was to say medium fertility plus half a child per woman. And that's in a way a bit arbitrary, but it's not crazy, right? If you think the total fertility rate in Canada currently is about 1.5 children per woman, you could think it's quite easy to think that it could reach 2, right? It has been 2 in the past. It could go back up to 2, which is close to replacement level. However, that's not what the variant is saying. The variant is saying that not just at some point in the future in Canada could it reach half a child higher. It's saying in every country, in every time point in the future, it will be half a child higher. And if you think probabilistically, that's many events, none of which is terribly likely, and it's saying they will all happen. And if you look at the intersection of all these events, of course, it's quite unlikely. But demographers weren't thinking probabilistically in those days. So, and these scenarios don't really work terribly well. They've no probabilistic basis, and particularly they can be quite implausible over multiple projection periods, as I've mentioned. So some other issues with traditional methods, they're methods from the 1940s, like Model T Ford, if you like, could still run. They're successful overall. They hadn't really been updated all that much. But the Achilles heel is the reliance on expert assumptions about the future, or expert forecasts of the future. And it turns out experts and expert panels are very good for many things, very important for science, right? They're very good at assessing the science, identifying what science is important and relevant for the problem at hand, identifying the relevant data, assessing its quality, and designing models. But the one thing that experts are not good at is producing forecasts from scratch. And just this was first found out by Paul Meehl, a psychologist, Paul Meehl, in 1954, so it goes way back. And he looked at medical prognosis and diagnosis. And the standard approach was, the physician, the specialist, the great man would look at a patient and say, okay, based on my experience, here's the prognosis. What Meehl did was he compared the prognoses from the leading specialists and so on with very, very simple statistical rules of thumb. And he found that the statistical rules of thumb beat the clinicians in this case. And of course, that was greeted with disbelief and outrage at the time. And for about 30 years, there were all sorts of studies done in an effort to debunk this work. And actually in 1986, I think Paul Meehl wrote a kind of article whose title was, it was Causes and Effects of My Disturbing Little Book. So he was saying that essentially all these studies had really confirmed his results. And now, of course, in medical science, you go to your doctor who will give you prognosis, of course, but that prognosis won't be based on his personal experience, although it might be, of course, influenced by that, but it'll be based on the medical literature, which in turn is highly statistical. So medical practice has integrated this insight for a long time, whereas demographic practice is really only starting to do so. The Open and Vopal in demography showed that demographic expert forecasts were poor, had been very poor, specifically for life expectancy over the entire 20th century. Philip Tetlock, who's a psychologist and political scientist, studied expert political forecasts by political experts, professors of political science, newspaper pundits, and so on. And he found they were terrible. And he summarized this by saying this famous phrase that dart-throwing chimpanzees would do better than the experts. And of course, they're not probabilistic. So one might think, why do we need probabilistic forecasts? And you know, this was the first person to call for probabilistic forecasts was Nathan Keyfitz himself in a 1972 article in the Journal of the American Statistical Association. And he also produced the first probabilistic forecasts some years later, I think 1980, 79. This is National Research Council in 2000, where there was a consensus along those lines. Basically, we need a general assessment of accuracy that has become, you know, expected in most estimates that are scientific or policy relevant. Just, you know, is this an accurate estimate, or is it really a broad kind of thing? Secondly, for assessing changes and differences between outcomes and expectations. So that's also important. If we see a change in the fertility rate, for example, is it just the kind of thing we'd expect in the normal run of such fluctuations, or is it really something different from that, a structural change that we should be paying attention to? And finally, making decisions that avoid or minimize risks. And an example that I'm quite familiar with that is very common in the United States is the decisions to close schools. So, you know, the school boards, as you probably know, in the United States, the schooling system is very decentralized. School boards in particular areas, for example, cities, run their own schools. They're not mostly run from federal or even, in some cases, state governments. It's very common for a demographer to come and say, I forecast the number of school-age kids will go down, for school board to close schools. And this happened in my own city of Seattle, where in the 1990s, this was done. A lot of schools were closed. There was, you know, huge unhappiness, which spilled over into, you know, demonstrations. The school board members lost their jobs at the subsequent elections. But it turned out, instead of the number of kids going down, the number of kids went up. And they had to scramble and try and reopen schools or have, you know, trailers or temporary buildings and so on. So it was a big disaster. And the school board president actually was interviewed later, and he said, if we'd only known that demographers could be wrong, we wouldn't have closed the school. So it's very important to not close a school until you're pretty sure that you won't have to reopen it again. And the best way, the most efficient way of knowing that is to have not just your best estimate of the number of kids, which probably a forecast of a decline was probably not unreasonable, but a probabilistic forecast would have said, well, there's a good chance that it won't decline. So you should wait until you're fairly sure before making a decision like that. So probabilistic population projections, just to give you an overview, we do probabilistic projections of each of the three components of population change, which are fertility, mortality, and migration. We develop a statistical model of, for example, total fertility rate. And from that, we draw a sample of trajectories from the joint predictive distribution of future total fertility rate for each country and period in the future. And in this case to 2100, but we'll see how it goes to 2300. That gets converted to age-specific fertility rates, and a similar approach is taken for mortality and migration rates. The projection model, the core component model, which is deterministic, is applied to each sample. So then we've got many possible population futures of the world, which represent a predictive distribution, probability distribution for any population quantity of interest. And one advantage of a statistical approach over, for example, an expert-based subjective approach is that the method can be assessed objectively. So we can hold out, for example, a recent period, for example, the last 30 years, we could say, let's pretend we're in 1990, apply the method to the data from 1950 to 1990, develop projections of the 1990 to 2020 period and compare it with what actually happened. And, you know, this, it did turn out this was substantially better than the UN's previous method, and the intervals that came out of that were reasonably well calibrated, in fact, very well calibrated. So I want to give results of this, and if there's time, I might drill down a bit into the TFR model, although time is kind of running, so I may not as well. So just results, the world, this is forecast of world population growth, and we see here the red. So on the x-axis, we've got time from 1950 to 2100, and I'll talk about the much longer term afterwards. And then on the y-axis, we have population in billions. And this is kind of present time. Here we have the past, and here we have the future projection with the median projection in red, an 80% interval in dark blue, a 95% interval in light blue. And here are the traditional scenarios in the dashed lines. We can say they're way outside probability interval. So the projection for 2100 current world population is about 8 billion. The UN's approach, which is forecast developed using the methods I'm describing here, is 11 billion, with a predictive interval from 9.5 to 12.5 billion, roughly. And just for comparison, the International Panel on Climate Change's most recent scenarios have populations that look like this. So they kind of do span this area, but they're on the low side for the most part. So these four are the ones that get the most attention, and they seem to be on the low side in terms of forecasted population. So it could well be that actually the IPCC projections are conservative in that obviously bigger populations emit more carbon, and this just compares the UN Bayesian projections with the IPCC. This is, I think, it's the 9.0. Okay, one important thing is where will the increase happen? And here we see the increase by continents, and here with the biggest continent in terms of population is Asia, and we see that it'll go up, peak in the middle of the century, and then probably go down, although there's some possibility it might level off or it might decline faster. So here, this is North America, Europe, and Latin America, which are much smaller populations. But Africa, this is Africa, and this is important now. It's 1.3 billion. Projection is it would reach 4.3 billion, so triple in the rest of the century. And range is about 3.5 to 5.5 billion. So there's quite a lot of uncertainty, but very little uncertainty about the fact that there is a rapid increase. And I'll just mention there's a fertility decline in Africa, but there's been a slowdown or stall in the rate of fertility decline, which is probably at least partly due to unmet need for contraception, which continues to be present. Okay, and this is some of the kind of commentary, and this is an article in Science that was basically reported on these results in their first version, and this is collaborative between our group and the UN, and this was the coverage from The Guardian, for example, where and one thing that there's a kind of an old trope that says, oh, ordinary people don't understand probabilities, but actually the media were very interested in the probabilities, and The Guardian featured this in the probability in its headline. So I don't believe for a second that people don't understand probability. I think they do, actually. Okay, so I don't know if I'm not really going to drill down to the TFR because I want to get to the so I think given just the the rate at which time is going, I will kind of skip over more detailed description of the TFR model. I'll just very briefly say it divides the history. The history of fertility is divided into 3 parts. So this is the total fertility rate in the Netherlands from 1850 or so to the present in 5-year periods. And we see there are 3 phases. There's a pre-industrial phase, and then there's phase 2, which is the fertility transition and decline to below replacement level. And this basically has happened in all countries, or at least started in all countries. And then finally, we've a 3rd phase, which is a low fertility post-transition fluctuations after it. So basically, TFR goes down and then stops declining and bottoms out, fluctuates. And this has happened in all countries. And there's a lot of debate in demography about why this has happened. There is essentially no dispute about this characterization. And I think we were the first to actually sort of express it in terms of phases, but that was just kind of formalizing a discourse which is common to essentially all demographers. So I think I'm going to just skip over this, because except to say that it's a Bayesian model is used, a Bayesian hierarchical model with estimation using Markov chain Monte Carlo for the phase 2 transition. Between country correlation in forecast errors is included. And then the phase 3, the post-transition period is modeled using, which has been observed so far in 40 countries, most of the developed countries, not officially Canada, although Canada will probably enter it very soon, but also some East Asian countries. And the Bayesian hierarchy, there's a Bayesian hierarchical autoregressive model for the time series. So I apologize for just skipping over this so fast in the interest of time. This is just one example. So France, this is the end of the French fertility transition. And then France has been in the phase 3 for a while. Its current TFR is just below 2. And here we have 3 possible projections, 3 possible trajectories from the future of French fertility. We see there's one that kind of goes up and actually comes down. There's one that goes down and comes up, and then there's one that kind of fluctuates around. If we look at, here we see a lot of trajectories, and here we see the predictive median, which is this red line here and is flat. Here we see 80% interval, 95% interval. And there's an interesting thing here, which is, one thing we know for sure is that the future is going to be pretty jagged, it's going to fluctuate. But the median is completely flat. And so if you think deterministically, you'd use this and this would be your forecast. But actually, one thing we know is that the future is not going to look like this, even though this is the best estimate of the future. So that's a kind of a difficult thing to communicate. And it is an interesting kind of mathematical thing which has important implications and is hard to get across. So, okay, to get to the very long-term population projections. So the first step, the UN method, which was developed by our group, goes to 2100. So the first step was to say, okay, we want to go to 2300. It's a statistical model, probability model. We can just extend it, right? So we extended it. The problem is that the 2300, so 2100 is 3 generations into the future. So it's fairly reasonable to think that statistical regularities will continue. 2300 is 10 generations into the future. It becomes a lot harder to make that argument and to say that the statistical model will hold without any modification. And the resources for the future, basically to assess that, and at least there was a feeling, and we felt that it was important to get to have that validated and reviewed by expert opinion. And as I said, experts are very good at reviewing models and reviewing outputs. They're maybe not so good at just producing forecasts out of their heads. And this is the panel of demographers, and if you're a demographer, you probably recognize this is really leading people in the field, and you probably recognize some of these names if you're maybe all of them if you're a demographer. So and most of the perhaps all of the groups involved with seriously doing research on population projections and related areas are represented by leading people in this group. So they reviewed it, and it was extraordinary review. There was a day of meetings, but also each person here produced a written report on on the projections and what was good and bad and what could be improved. And so many comments and suggestions were made. In fact, the overall conclusion was that this was probably about as good as could be done, although it's a very daunting task. But there was one consensus view, which was the UN method gave a 95% interval for world average total fertility rate in 2300, with an interval from 1.66 to 2.23 children per woman. And the main consensus of the panel was that the upper bound was okay, but the lower bound here was too high, that actually it was possible one could easily conceive of world fertility rate being lower than 1.66. And they recommended a lower bound for this to be 1.2. And so we revised the method, adding a world level random walk with drift to all the projections. And the result was a 95% predictive interval for world TFR in 2300 that went from 1.2 to 2.23 as desired. So just some results from this. So this is world population. On the x-axis, we've got time from 1950 up to 2300. And this is 2020 here, this is 2100 here. And then on the y-axis, we have population in billions, and we're around about here at the moment. Well, we're actually, sorry, we're here. And the black is the past from 1950 to 2020. The blue here is the UN projections to 2100, which almost exactly, of course, parallel what we're doing. And then the red after that is our projections from 2100 to 2300, with the median here 80% interval, 95% interval. So one can say population is likely to continue rising for at least most of this century. It's likely to level off in the 22nd century and to decline in the 23rd century. For 2300, the median is 7.5 billion, so pretty close to where we are now, actually. And the 95% interval is very wide, goes from 2.3 to 20.5 billion. Very wide, but, I would argue it's not infinitely wide. To saying population is likely to be below 25 billion, it's not saying nothing, it's saying something, or that it's likely to be at least 2 billion people. And it's appropriate that the uncertainty be wide when we're looking that far into the future. And because it's asymmetric, it's exceptionally important to take account of this when assessing the social cost of carbon. One can look at continental projections. Here we have Africa, where as I've said, there's a very dramatic population increase projected for this century, but actually it is quite likely, it will for sure peak probably around 2150 or later in the 22nd century. So it's not, because fertility in Africa, even in high fertility countries, is going down, that process is going to continue. It will eventually peak, although later than elsewhere. Asia, we see a peak here coming, quote, soon, around 2050, and then a substantial decline. Europe is in this interesting point where it's right at the peak. Population has been increasing, and it's about to start going down fast. And European population is going to be aging fast. Latin America and the Caribbean looks like Asia. Northern America, actually, our prediction is a little bit lower than the UN's one because of our we're doing probabilistic forecasting of migration, and in the long run it's likely to level off, reflecting the aging, North America its population has been growing and will continue to grow largely because of immigration, but because the population of the rest of the world is aging, most people migrate internationally between, say, 18 and 32. The proportion of the population that's in that age group is going to go down, so the number of migrants to anywhere, but notably to North America, is going to go down. So, okay, so just a few points of discussion. One thing that's not explicitly included in our model or in our method for population forecasting is climate feedback. And in other words, population has an impact on climate, obviously, but population has an impact on climate, but climate can also have an impact on population, and that's not explicitly in our model. And there are a number of reasons for that. The first is that the science is not yet fully in place to quantitatively assess the potential impacts of climate change on future fertility, mortality, and migration. And beyond that, I would say, to the extent it is, these impacts are probably smaller than people think for the purposes of population projection. So the one that's best understood is the impacts on mortality. World Health Organization has projected that climate change is likely to lead to 250,000 excess deaths per year in the future. Of course, that's huge. That's humanitarian disaster. But in terms of the impacts on overall population numbers, it's quite negligible because, 100 million people die a year. If you increase that by 250,000, you're not going to change population trajectory all that much. There's not much is understood about the likely effects of climate change on fertility. And migration is perhaps the one that's talked about most in the media, and there's no doubt climate change will have an impact on migration. Most of that will be actually internal migration, not international migration. So, for example, the biggest climate event in North America to date was Hurricane Katrina, which emptied out, the whole of New Orleans was abandoned, but people, they didn't go to Mexico or Canada from when they left New Orleans. They went to Mississippi or to Texas, and that's likely to happen in other events. There are some exceptions, which are like island nations, which might disappear completely, but these have small populations. So although it's callous to say it, in the broad sweep of looking at world population, that doesn't make much of a difference. And the approach, and we'd argue the approach implicitly does include some effects of climate change on population. It's estimated from data for 1950 to 2020, which is a period at the era of climate change. It's the era during which the climate warmed by 1 degree Celsius. So essentially, to some extent, it's included in the data that are used. It includes density-dependent constraints, which imply basically if the population in any trajectory gets too big, it will be, that'll be corrected and discounted. And the continuing migration from countries most affected by climate change actually is baked in here from this. So as an example, the large country that is most likely to be affected by climate change is Bangladesh because of flooding, likely flooding. And our methods project that from 2050 to 2300, the population of Bangladesh would go down by 84%. And that likely reflects climate change. So but there is an implicit assumption, which is that the basic demographic patterns of the last 150 years will continue. And these are, first, the fertility transition will continue in high fertility countries. We'd say pretty much all demographers would agree on that. And the fertility transition won't be reversed. So you're quite unlikely, right now, the total fertility rate in Canada is 1.5 children per woman. You're unlikely to get to a situation where that's reversed, where that goes up to 5 or 6 or 7 children per woman. And I'd say that's certainly a consensus among demographers and probably other experts. And second is that we'll continue to see, a steady improvement in life expectancy, perhaps with some stalls and reversals, but that'll be the broad trend. So to try and summarize, we extended the UN's methodology for probabilistic population projections from the present 2100 to 2300 to also incorporate expert review. So we kind of acknowledge that a purely statistical approach, while we would argue that it's, you know, under supervision, it's largely, it works well up to 2100. It does need expert review and revision for going much beyond that. And this led to a reduction relative to the UN's methodology in the projected lower bound for world TFR in 2300, which was the main difference made by the expert review. And world population is likely to continue to rise for most of this century, to stabilize by the early 22nd century, and to decline in the 23rd century. And there's large but finite, and I would argue appropriate, uncertainty about what will happen in 2300. And these projections are currently being incorporated and being used as part of the US government's assessment of the social cost of carbon, which in turn will be used to make decisions about all projects of the federal government going forward. So just some references. The long-run population projections paper was just published very recently in the International Journal of Forecasting. The broader social cost of carbon estimation methodology is also just being published in the Brookings papers on economic activity, which in spite of its rather odd name is actually a leading economics journal. And the SCC results, which I can't really give any details about, are in a paper that has been submitted for publication. And for the probabilistic population projections, there's software available that anybody can use. It's the BasePop R package. Okay, so I've gone on a bit longer than I hoped, but thank you very much. I'm very happy to take questions. I will just go here, actually.
Thank you very much, Adrian. It's a wonderful talk.
Thank
I can't
you.
hear everybody applauding, but they are. So while we wait to see if there are any questions, maybe I'll just make a few comments. Firstly, I hope we have you back in person sometime soon, because I'd like to see some of the slides that you went.
Yeah,
they look pretty.
The more mathematical ones, yeah.
One question I was thinking of was this. You know, as you look at these projections, we are up to our ears in projections these days because of the pandemic. You know, people trying to figure out what's going to happen next. And we are confronted with two kinds of problems. When you mention scenarios, you know, that's in public health. Many people still like to use scenarios.
Yep.
But our time scale is, of course, not centuries or millennia. But we know that traditional methods essentially fall flat once you get past 30 days or 60 days. I mean, we're talking about months. And there I've seen two different ways of approaching this whole problem. And one of them looks a lot like what you're doing in the long term. So let me transcribe the kind of question we're looking at in your context. How would you incorporate into your model either an extreme event or some sort of systematic policy intervention or something that just basically changes the way we live?
Yeah, and that's a really great question. To some extent, I think the extreme events, I mean, there's two things about the extreme events. There are two kinds of extreme event. One is the extreme event that ends civilization as we know it, like nuclear war kills 90% of the population. And to some extent, there's a sort of assumption, you know, if that happens, then there's no point in, you know, population projections aren't going to be used. We'll be like, you know, scrabbling around for bits of food and so on. So there's a kind of assumption that in some very broad sense, civilization as we know it, or a little bit like we know it, will continue. Right, so to some extent that could happen, but or things like that could happen, but you know, any kind of planning and so on is sort of conditional on that. You know, the meteor wipes us all out, that kind of thing. Then of course these projections would be wrong, and we'd be, you know, like the dinosaurs or whatever. But the other kind of shock, which I think is important to include, is, events that have big demographic impacts. And so one can think of pandemics, and the big ones are pandemics and world wars or wars. And actually the estimation period does include, and beyond that, we have actually data back to pretty systematically back to the beginning of the fertility of the demographic transition in 1870. And that period does include a lot of shocks. So it includes World War I, World War II, it includes the 1918 pandemic, and it also includes quite a few other pandemics, which, like various flu pandemics that killed millions of people. And the biggest demographic event was the 1918 flu, but close behind it was the HIV/AIDS pandemic. And COVID is maybe shaping up to be the third one. World War II is kind of maybe also on the same, killed about 50 million people. So it's on the same kind of magnitude. It's kind of interesting that if you look at, there's been, since about the mid 19th century, there's been a steady increase in life expectancy around the world. And if you look at the impact of these shocks, you see there's a blip where life expectancy goes down, but then it resumes after a few years. It resumes an upward trajectory. So actually, the effect of these cataclysmic events is a lot less on overall population numbers than one might expect. So and that is kind of looking at the numbers. That's the case. So I think we've incorporated, and terms of wars, 1950 to 2020, there have actually been, if you define a war as something that kills at least 100,000 people, there have actually been 40 wars of that kind. So 40, major wars, because 100,000 people is a lot. So although in the let's say the developed world, we think of that as being a period of peace, because there haven't been many wars in the developed countries over that period. It has not been really a period of peace at all, and that is factored in because it's in the estimation period. So I think that's. But obviously, that's a kind of reflection it's important to keep on thinking about these questions, because and having thought about them, I feel fairly comfortable with coming down there. We have we've sort of built in long tail distributions for sex gaps in life expectancy and changes and so on, which account for some of these or can account for the possibility of these events, and I feel fairly comfortable that does account for, in a reasonable way, for what one could expect. But there's always the possibility of doing better with methodology. And this is actually the first. Nathan Keyfitz was the first to produce any probabilistic population projections. I think this is the first math that has been produced that for all countries, and certainly the first to become the basis for official population projections worldwide. So in that sense, it's kind of a first draft, and I think that there's all kinds of potential for methodological improvements. And indeed, a lot of demographers, statisticians, mathematicians, and so on have got interested in this and are working, not from necessarily from our group, but just around the world, and are doing great work on, improving what we're doing. I think in science, somehow the greatest success is if you become obsolete and other people improve on what you've done. So we're not there yet, but hopefully there'll be improvements.
Wonderful. So I don't see any questions in the chat. Maybe I just make one further comment, namely, your talk is really very, very apropos. I said partly referred to the pandemic, but partly also because the Fields Institute, together with other Canadian mathematical institutes, is about to start a big project on climate change and mathematics. I think your ideas would be very, very relevant and interesting in that discussion, and I hope we will be able to engage you in that.
Absolutely, I'd love to. Yeah. No, that's great news, actually. Yeah, and I think there's a lot of mathematics comes in. I see. Oh yes. yeah, there is a question actually in the chat here. Maybe should I reply to it?
Sure.
The question, I'll just read it. It's from Jordana Feldman. It says, I think you said that your projections for the 1990 to 2020 growth was better than the UN's 4%. How did it compare on a country by country basis? So actually, so yeah, that isn't exactly what I said. But a lot of our contribution is actually assessing uncertainty, which becomes, as the question suggests, becomes really important in when one starts to look at individual countries. So, but the comparison, so to some extent, comparing, our methods have been used by the UN, and we've been, collaborating with the UN. So there isn't really, it's kind of the same thing. But if you compare our method with the UN's previous method, I think you find pretty systematically that the projections were better. We looked at it for mortality particularly, and the mean absolute error was about was almost halved actually by the statistical method relative to the previous expert method. But of course, the UN has integrated our approach, so they're by definition doing as well as we are. And on a country by country basis, it becomes more important because you've got a lot more variability when you look at an individual country than the world as a whole. What was kind of impressive in that is that although things were off by more than 4% for some individual countries, on average these errors kind of averaged out. So the overall approach on average was there weren't really systematic biases. It was more in unpredictable ways. Some countries were, going up and others were going down. Yeah, okay. It's
very good. Yeah. I don't see any other questions in the chat. Jordana, by the way, is field staff, and she's helping us to curate the questions.
Okay, so she said it's from the audience. Okay, so somebody in the audience.
Very good. Okay, so I don't see any further questions here. Then I think what's left is for me to thank our speaker again for a really stimulating talk. I think you started us thinking about we're eager to read some of these papers, and hopefully engage in further conversation with you on this very interesting topic. So
thank you. It's been
thank you very much, pleasure. Adrian, and let's thank Adrian again.
Thank you so much for the invitation. It's been great.
And once again, I hope to see you soon in person at the Institute when we can chat further. Very good. Thank you very much.
Indeed. Okay.
And thanks everybody for joining us. I hope you got a lot of out of the talk as much as we did. And feel free to join us for further Fields Institute events. We do have many events meant for the general public, also technical events. Just stay tuned to the website and you'll see all the announcements there of upcoming events. Once again, thank you for joining us and keep well. Bye.
Bye.